The work I'll be discussing here was done in the last several years. It's been done actually in collaboration with several groups around the world. But the drivers behind most of what I'll tell you today was done by these three young people. So Sam was a postdoc at MIT, now has moved to Cornell as a postdoc. Yoni is my former student from Weizmann, who's now a postdoc at Stanford, and Xiaoyu Wang is a postdoc with me now in Chicago. Just to set the stage, I'm going to talk about quantum criticality. There's quite a lot which is known about quantum critical phenomena in insulating materials, so insulating or gap systems. These phenomena are quite rich and interesting. To some extent, they can be mapped to a classical critical phenomena in one dimension higher, but the analogy is not complete. But nevertheless, this is a problem that we know a lot about. We read about it in Subir's book, for instance. In contrast, there's much less which is understood about quantum critical phenomena that occur in a system that has a Fermi surface. So I'll get into some reason for that, but this is basically what this talk is going to be about. Again, as you know, this problem is not just an abstract theoretical problem. There's a lot of indications that some form of quantum critical phenomena is occurring in many types of strongly correlated materials. Here I've highlighted especially high-TC superconductors. So these are two different families of high-TC superconductors, the cuprates and the iron-based superconductors. They're microscopically very, very different from each other, but nevertheless there's kind of this striking similarity, qualitative similarity between these phase diagrams. And there's some commonalities between these materials, different correlated materials. So one of the common features is the complexity of the phase diagram. So by that I mean that by relatively small changes in parameters like composition, magnetic field, or pressure, you can drive the system between different kinds of electronically ordered states, and including, of course, high-TC superconductivity. And therefore, it's quite natural to ask what's the role of quantum critical points between these different phases in the behavior of these materials. Moreover, if you just look at the phase diagrams of these materials, especially if you look here, okay, so this is the phase diagram of one of the iron-based superconductors, and what's plotted here in color is basically the log derivative of the resistivity as a function of temperature. Okay, so you see here this very pronounced fan-shaped red region, so red corresponds to 1, means that the resistivity in this regime is approximately a linear function of temperature. Okay, whereas if you go far away from this point, the exponent comes closer to 2. 2 is the value which is expected for a Fermi liquid. Okay, so it looks like there's some sort of anomalous metallic state that occurs centered in this region of the phase diagram. And with some imagination, you can imagine that this fan-shaped region is converging towards a point where this antiferromagnetic phase is actually going away. Okay, and this type of behavior is seen actually in many different systems, and it really invites you to think in terms of some underlying quantum critical point which is responsible to this big portion of the phase diagram that seems to show some sort of anomalous metal. Okay, so this has led people to think about quantum critical phenomena in metals for many years, and that's going to be the topic of this talk. Okay, so this is my plan. I'll describe briefly the types of models that people write to describe quantum criticality in metals. My main approach to this problem would be quantum Monte Carlo, so I'll show some of our quantum Monte Carlo results for different physical quantities. And then in the last part, I'll focus on transport properties, which are in some sense the most challenging to calculate, but also the most interesting. And I'll show some of our results for a particular type of critical point, the Ising-Dematic critical point. Okay, so I'll focus on two particular types of order parameters in this talk. We believe that their behavior is quite generic, but the results I'll show are specific to these types of critical points. One of them is the so-called Ising-nematic quantum critical point. So here we imagine a system that has C4 symmetry that lives on a square lattice, and at some value of some Hamiltonian parameter, the system breaks spontaneously this 90-degree rotational symmetry down to a 180-degree symmetry. Okay, so there's an order parameter that can pick between one of these two configurations. That's why it's called Ising-nematic. Again, what happens in a metal that undergoes such an Ising-nematic transition is that the Fermi surface in the disordered phase would have the same symmetry as the lattice, so it might look like a slightly distorted diamond, or like this red curve. Okay, and when you go into the ordered phase, the Fermi surface would actually distort according to the configuration of the order parameter. So it would either become elongated along the x or the y directions. So a property of this type of order parameter is that it occurs at q equals 0. It's uniform in space, and therefore it couples very effectively almost to the entire Fermi surface. So the fluctuations of this order parameter near the critical point would scatter fermions effectively almost everywhere on the Fermi surface, with the exception of these special points, the diagonal points, where just by symmetry, because of the form factor of this order parameter, the coupling actually vanishes to leading order. Okay, so we expect to have some special points where the fermions to leading order are decoupled from the order parameter fluctuations, but everywhere else the fermions would be very strongly coupled. Okay, so that's one type of critical point I'll discuss. The other type is in antiferromagnetic quantum critical point, or spin density wave critical point. Okay, so here the difference, the important difference for me would be that the ordering occurs at the finite wave vector. Okay, in this example, it's pi pi. So it's this kind of nail antiferromagnet. And this type of ordering would be characterized by a scattering of fermions resonantly in two spatial dimensions, only at special points on the Fermi surface. So there's a discrete set of points that are connected to each other by this ordering wave vector. Fermions close to these points would be coupled very strongly because they can scatter resonantly, and points very far away are off-resonant, and they're going to be much less strongly coupled to the order parameter fluctuations. Okay, so here most of the actions would occur we expect near this discrete set of hotspots, unlike here where there are cold spots where nothing happens and everywhere else the Fermi surface is hot. Okay, so these are the two problems I'll discuss here. Okay, so let me describe briefly the types of theories that people have been writing for a very long time in order to describe these type of phenomena. Okay, so the theory is trying to capture the low energy degrees of freedom close to the quantum critical point. That there are two types of degrees of freedom. One is the fermions close to the Fermi surface, the usual quasi-particles that form a Fermi liquid away from the quantum critical point. The other is the long wavelength and low frequency fluctuations of the order parameter field that are going soft when you tune the system to the critical point. Okay, and these two types of degrees of freedom would have would strongly couple to each other and form our quantum critical metallic state at the critical point. Okay, so here's the type of action that people write. So there's an action for the fermions, which is just free fermions with some dispersion. Okay, there's an action that describes these order parameter fluctuations. So that's a bosonic order parameter. And for that, we can write the usual Landau-Ginzburg-Wilson expansion in powers of the order parameter and the gradients of the order parameter, because we expect that close to the quantum critical point, the order parameter is small and its fluctuations are slow. Okay, so we just write the usual expansion. And for the interaction term between these two types of degrees of freedom, we just write the lowest order allowed term, which is this so-called Yukawa term. So it's linear in the bosonic order parameter and quadratic in the fermions. Okay, there's some symmetry form factor here. For instance, in the case of the antiferromagnetic order parameter, this would be a vector, and it couples the spin of the fermions. Okay, and there's only one coupling constant in the theory, which is this alpha, the so-called Yukawa coupling. Okay, so that's the theory. It's kind of it's actually a pretty simple quantum field theory, but it turns out that it's very hard to analyze. The reason it's hard is because of the fact that it has so many low energy degrees of freedom open, namely the entire Fermi surface is full of low energy degrees of freedom, and these mix very strongly with the order parameter fluctuations. Okay, so it's useful, before I get into numerics, to actually have a very simple, simple-minded perturbative analysis of this action, okay, just to have a concrete picture in mind. So let me go through that. Okay, so what I'm going to do is, artificially, I'm going to take the Yukawa coupling to be small. Okay, so it turns out that I can choose this alpha squared to have basically units of whatever density of states. So this is my dimensionless parameter, and I can make that artificially small. Of course, this is a relevant interaction, so it's going to become strong close to the critical point, but nevertheless, let me start from weak coupling and high energy so that I can control perturbation theory, and then ask what's the sequence of crossovers that occurs as I lower the energy more and more. Okay, so at very high energies, this coupling is weak, so it basically doesn't do anything. So I have basically the two decoupled theories, the critical boson, which has the usual Wilson-Fisher type criticality, and I'm analyzing it in two spatial dimension problems. So it has it equals 2 + 1 dimensional Wilson-Fisher criticality. That's characterized by z = 1. The dynamical critical exponent is 1, and the fermions just form the usual Fermi liquid. So now, as I lower the energy, it turns out that the first thing that happens is that the order parameter fluctuations become strongly Landau damped by the presence of the fermions. Okay, so that's been known for a long time. That's precisely what the Hertz-Millis-Uriah theory describes. Okay, so the order parameter fluctuations become strongly damped as a result of coupling to the electron hole pairs. But it turns out that in this regime, the feedback of the order parameter, of the coupling to the order parameter on the fermions is actually parametrically weaker. So at weak coupling, there's a well-defined a parametrically big window where the dynamics of the system is described by a strongly Landau damped bosons coupled to coherent fermions. Okay, so this regime is actually well understood. And then there's a lower energy scale. So what the analysis I'm describing here is specific for the Ising nematic. It turns out that for the antiferromagnetic magnet, it's a little bit different, but qualitatively similar. So here it turns out that the onset of Landau damping happens at a scale which scales as mod alpha, this Yukawa coupling, whereas this lower scale actually scales like alpha to the 4th power. So at weak coupling, there's a big parametric window between them. And in this scale, actually several things start breaking down. The first thing is that the fermions also become strongly damped. So the scattering of the fermions off the order parameter fluctuations, which is captured by the self-energy of the fermions, becomes of the same order as the frequency or the energy. Okay, so this means that Landau quasiparticles basically stop having a well-defined meaning. At the same time, the superconducting fluctuations of the fermions, which are mediated by the attractive interaction, which is basically mediated by the order parameter fluctuations, also become strong. Okay, so if you try to estimate a green field TC coming from this regime, you'll find that TC is actually of the same order as this non-Fermi liquid scale. So we have a competition between these two opposing effects. One is that the fermions become more and more incoherent, and the other is that superconducting fluctuations become strong. And it turns out that it's this competition which is actually very hard to describe in a systematic way. Okay, so this is the non-perturbative regime. This is really the regime that we don't have good control of.
Can I ask
yes.
Qualitative question about the intermediate regime? So if I'm allowed to look as a function of temperature,
Yes.
Is the statement that in this intermediate regime, if I were to look at the specific heat, right? So I would see a contribution to the specific heat that originates with weakly interacting, if you like, fermions with linearly specific heat and the overdamped boson T to the 2/3 specific heat?
So yeah, this is.
Are there two specific heats?
Yeah. So ask me in a couple months, or ask Andy.
I think there's only one.
I think there's only one, but that's what I'm trying to get to is that this picture that the fermions are underdamped or coherent. I thought that question was asked, before you and I were in physics.
Yeah.
People,
yes.
by explicit calculations, people had demonstrated that I'm thinking of Young-Bit Kim or somebody like that fermions are already overdamped in that regime.
Yeah. So if you just do this analysis, this is what you get.
Okay. All right.
Okay,
We'll come back
yeah,
in 2
yeah.
months.
So right. I mean, I believe. Okay, right.
This third axis, right? How close you are to the criticality?
This is at criticality. That's right.
Oh, this is exactly.
Yes. Yeah. That's right. It's an important point. Okay. This would serve as an additional cutoff if you have another axis. Yeah. Okay. Yeah. Right. So yes. So I believe that people knew this, but I just learned that there is this well-defined regime, and I think what's the specific heat there?
But what is the signature is that the spectral function, the single particle spectral function, does not show quantum critical damping?
Yeah, so I mean, it does show quantum critical damping. It's just that it's still coherent. Okay, I'll actually show you some consequences. So for instance, the scattering rate is anomalous, right? So because the scattering rate of the critical fluctuations, we should compare that to 0, which is the scattering rate of free electrons, and that's always strong. Right, but if you ask what's the, for instance, what's the effective mass renormalization, that's small in this regime, or what's the renormalization of the quasi-particle weight compared to 1, so that's 1. Okay. Right. Okay, so right, so that's the setup, and this understanding the properties of the low temperature regime is the hard problem. Okay, so this is where a lot of effort of very, very strong theorists has been invested, and different approaches often actually give different results. Okay, so my approach to this problem would be quantum Monte Carlo. So the strategy here, as many of you know, is to integrate out the fermions exactly, which can be done for this for these types of actions because the fermions are quadratic. So what you get is an effective action for the bosonic degrees of freedom that looks like the bare effective action times a piece that comes from integrating out to the fermions, which is in the form of some a determinant of an action matrix. And fortunately for many of these problems describing quantum critical points, it turns out that this effective action that you get is actually free of the sign problem, meaning that it's a real action. Okay, for instance, for the isokinetic case, that's very easy to see. So the reason for that is just that the isokinetic order parameter couples in the same way to spin up and spin down electrons, so and it's real. So when you integrate out the fermions, you get a determinant of the spin up ones and another one for the spin down ones, but these two are the same, okay, and the real numbers. So the product is a non-negative real number. For the antiferromagnetic case, we're actually not as fortunate. The reason is that here the order parameter actually couples to the spin of the electron, so by definition it couples differently for spin up and spin down electrons. However, it turns out that you can modify the problem a little bit. So if you just try to formulate the problem as I wrote it before, with just one flavor of fermions coupled to a magnetic order parameter, you would actually get a severe sign problem. But it turns out that there's a modification of the problem that is actually sign-free. So if the Fermi surface is such that the order parameter always, at the hotspots, always scatters you between one flavor of electrons, say forming this red band, to another flavor that forms this blue band, then it turns out that this interflavor structure actually prevents the sign problem. It turns out that the action matrix in that case has an effective time reversal-like symmetry that guarantees that this action is actually real. Okay, now,
Can I just ask, so
yes.
are the conclusions of this modified problem supposed to be conclusive about the other one
Right.
also?
Yes, yeah, let me address that. So, of course, the question is, when we modify the problem, have we also modified the properties of the solution? And I can give you several reasons why I believe that it does capture the more generic behavior, but at the end of the day, the answer is I don't know. We don't know how to do the simulation in the other case. Okay, so the theory predicts, and also everything that we see is consistent with the statement that the behavior near the critical point is really dominated by the vicinity of these hotspots. So that implies that if you capture the structure of the Fermi surface close to the hotspots, everything else is kind of irrelevant. Okay, so therefore you expect two problems. One of them with two flavors and the other one with one flavor. As long as the geometry of the Fermi surface close to the hotspots is the same, we expect these two to have the same critical properties. Again, you can add other terms and see that they're subdominant. Right. So that's really the reason why we propose this. Now, the other argument I have for this is that right. So this wouldn't be the right model for something like the electron-doped cuprates that really have only one Fermi surface. But in other physical systems, like the iron-based superconductors, you do actually have multiple bands, and the order parameter actually couples different bands, and it doesn't have hotspots within the same band. And many of the properties look qualitatively similar. And so you could say this is a good model for something like the iron-based superconductors, not for the cuprates. Okay, so there are some systems where this is the right structure. Okay, and a psychological argument, I would say that all the analytical theory pretty much on this problem was done on essentially this model. Okay, so in a hidden way, people just describe the vicinity of the hotspots and not portions of the Fermi surface far away. So at least it's, this numerics does apply directly to the quantum field theories that people have been studying. Okay, but that being said, of course, at the end of the day, I don't know. Right, other questions? All right, so yeah, so let me flash through some of our results. So I'll start from the Ising nematic critical point. Okay, so the first thing we've studied is the phase diagram. Okay, and we plot the phase diagram as a function of a parameter that we call h. It doesn't matter exactly what it is, there's some Hamiltonian, but h is basically a transverse field. It's a parameter that controls the degree of quantum fluctuations of the order parameter, and it allows us to tune through the quantum critical point, and the other axis is temperature. Okay, so we have a region where we have a nematic phase, we have a disordered phase, and this is our quantum critical regime. Okay, so as a function of this parameter h, we drive the nematic transition down. We couldn't go beyond this temperature, but it extrapolates to a quantum critical point here. Okay, and luckily it looks like the transition remains continuous. It doesn't go first order along this line. Okay, and this is for one particular value of the Yukawa coupling. As we crank up the Yukawa coupling further, it turns out that this critical point is actually covered by a superconducting phase. Okay, so the actual critical point in the middle is actually preempted by this superconductor. In this model, it turns out that this superconductor is an S-wave superconductor. In terms of its symmetry, it's an anisotropic S-wave in the sense that the gap is modulated as a function of the angle quite substantially, but it's still an S-wave. Okay, so now we can look at the correlations of the order parameter as a function of a temperature, frequency, wave vector as in this quantum critical regime. So that's what's shown here. Okay, so it turns out that over a broad range of parameters, the order parameter susceptibility basically collapses pretty well onto this very simple mean field-like form. Okay, so it's just the inverse of the susceptibility is just linear in temperature, linear in the deviation of h from h critical, and a proportional to q squared. You can see here the collapse of data with different parameters onto this form. Okay, so this is a very simple mean field-like form that was actually expected by from a Hertz minute.
H? It's a field?
H is a parameter in the Hamiltonian. So our Ising nematic order parameter is like a pseudospin, and this is like a transverse field.
Oh, this is the field.
Yes. Okay. So it basically drives us through the critical point. Okay. So right. So these are the static correlations. Omega equals 0. We've also looked at finite frequency correlations, basically the frequency dependence. So it shows very clearly that the bosonic fluctuations are lambda damped, meaning that the dependence of chi inverse on omega looks like mod omega. That's very clear. Okay, the exact the Q dependence of the prefactor of the mod omega is more complicated and more subtle, and I can describe it in more detail if you're interested. But we don't have, at the end of the day, we don't have a simple functional form for it. We've also looked at the spectral function of the fermions in this quantum critical regime. Okay, so what we can measure very directly from our simulations is this quantity. Okay, so it's the Green's function at imaginary time separation of beta over 2, which turns out to be proportional just to the integral of the spectral function of the fermions over a frequency window of order temperature. So that can be measured very directly without having to do any analytic continuation. So you see this quantity as a function of k here in the Brillouin zone. This is far away from the critical point. So here you can see the full pretty sharp Fermi surface. And this is what happens to it as you approach criticality. Okay, so this is for h near the critical point. You see that what happens is that along the diagonals, the Fermi surface remains pretty sharp, meaning that there's not a lot of broadening of the quasi-particles, but close to the corners, to the ends of the Brillouin zone, these so-called anti-nodal points, the Fermi surface is completely destroyed. Okay, so it becomes totally blurred, and this anisotropy is actually what you expect on the basis of the symmetry of the order parameter. So these are these cold spots where the coupling between the fermions and the order parameter fluctuations vanishes to leading order. Okay, so and these are the hot regions where the coupling is strongest. So here there's actually very strong damping of the fermions. If you look at the frequency dependence of the self-energy of the fermions in these regions, it actually shows a very unexpected behavior. It's best described by just m sigma is equal to constant, independent of temperature and frequency. This is very far from what we or anybody else expected. Okay, it basically looks nothing like the power laws that people would expect on the basis of naive scaling. Okay, so here are some results for the antiferromagnetic case. For technical reasons, most of our simulations were done for an easy plane antiferromagnet, for basically planar spins. We have now some preliminary results for the O3 case. Okay, and so far they look qualitatively similar.
Erez, just
Yes.
a question. So in the previous slide, what is the lowest temperature you were able to reach
Yes.
as compared to the basic electronic scale?
Yes, right. So
Because-
here,
yeah.
the maximum TC, so this is the strongest coupling we could go to. So the maximum TC here is 0.1 of T, of the hopping.
Okay.
So it's like 3% of the Fermi energy, you would
Yeah,
say.
okay.
And this is what really limits our temperature here. So this
is also in units of hopping on the left? or where?
on the left, this is in units of hopping, yes.
Okay, okay.
Right.
What's the largest size?
Right. So yes, so that's a good question. The largest size for the Ising nematic problem is 24 by 24. Okay, and everything I'm showing you here, we've checked is not sensitive. In this temperature range, is not sensitive to the system size.
So you basically don't see any scaling at all.
Yeah. Right. So we go to big enough systems such that we don't have strong finite side dependence. Okay. Yeah, so here I would say that the limiting factor for us is the temperature, not the system size. Okay, and what limits the temperature is actually TC, is the subconducting TC. Okay, this is actually taking the twice TC. Okay, so let me flash some results for the antiferromagnetic case. Okay, so here are a few phase diagrams. Here we have a different tuning parameter. It's called R. Okay, the Hamiltonian looks different, and this is temperature. And these phase diagrams are for different values of the Yukawa coupling. So you see the evolution of the phase diagram. There's a spin density with phase, which is driven to 0 as a function of R. And the critical point is always inside a superconducting phase. Okay, and the Tc grows as a function of lambda. In this case, it turns out that the superconductor is actually a nodeless D-wave superconductor. What that means is that we have this two-flavor or two-band system. The order parameter changes sign between these two bands, such that symmetry-wise, it's a D-wave, but it's a nodeless D-wave because on a given band, it never crosses 0. Okay, so that's what I just said. We've also looked at the order parameter correlations in the quantum critical regime. Okay, and basically for different couplings, it doesn't matter much. It turns out that here it actually agrees with this Hertz-Millis type form. So there's a Landau damping term, which is now independent of Q. Okay, it's just mod omega plus Q squared plus R minus RC plus some function of temperature. And you see here a collection of a large amount of data, all collapsing to this very simple form. So here it looks like over basically all the way down to Tc. It breaks down much below Tc, but down to Tc, this Hertz-Millis form simply works, with the exception of this coefficient, this temperature-dependent mass, which actually has a temperature dependence that we don't understand. It doesn't look like what you expect from Hertz-Millis.
What does it look like?
Yeah, so it looks more like T squared. Right.
Whereas all these other things would have a power of T which is lower than 2, basically.
All these other things are...
No, I'm on to the predictions of the various theories would give you a power law which is lower than 2.
Yes, exactly. Right. But by the way, for the Ising pneumatic, this is T. This is linear in T. We couldn't see a log, but probably that's not within our...
Okay, so that's what it's more or less supposed to be.
Yes,
logs,
yes,
right?
yes.
But for the AFM, not.
Yes, right.
Ask, so it's mostly for the previous hub, but it probably applies to this one. The expectation is that, so you haven't actually shown the plot of how the results, basically what is the self-energy as a function of Matsubara frequency? You keep saying that it's mono omega.
I'll show you, yeah.
But do you ever see Fermi liquid? Like with this numerical method, you should be able to see Fermi liquid and how it crosses over to this.
Yeah, we're looking at the Matsubara self-energy. So in that language, Fermi liquid would be linear, linear in omega, and we see that. We see that both away from the critical point, and even in the antiferromagnet, we see that even at the critical point, away from the hotspots. I can show it at the end. Right. Okay. So this constant behavior really seems to be tied to the critical point. Right. Right. So I have like 15 more minutes, something.
Yeah, 20.
Right. Yeah. We've gone in some more detail and asked questions like what actually controls the value, the maximum value of Tc close to the critical point for the antiferromagnetic problem. For that, we've actually tried a sequence of different Fermi surfaces, which are highlighted here. Okay, so one thing which is changing between, so there's some parameter in the band structure called delta, and that's changing. So one thing that's changing between these different Fermi surfaces is the angle between the two Fermi surfaces at the hotspots. Okay, so it's one of the Fermi surfaces is shifted such that this is the hotspot, and this angle between the Fermi surfaces at the hotspot is decreasing when delta decreases. You see that other things are changing as well. Okay, and this is the maximum Tc as a function of this parameter delta. Okay, so it's changing quite a bit. Okay, and the change is not due to the change in the density of states. You see here overlaid on that is the just band structure density of states. It has a van Hoff singularity because the Fermi surface goes from being open to being closed somewhere along the way, and you see that Tc doesn't really feel that. what DC actually does seem to correspond to is just this angle between the two Fermi surfaces. Okay, so this is a plot of TC max as a function of sine of this angle, and it has this linear, apparent linear dependence. This is actually what you expect from simple-minded Erez Berg theory, solving for the maximum DC at criticality from a quantum critical fluctuation that actually gives you this sine theta dependence. The way it enters is that the coefficient of the lambda damping term is actually proportional to 1 over sine theta. Okay, now this is quite exciting for us because this is the only knob we know to actually control TC, and in particular to decrease TC. If you extrapolate, this would mean that when the Fermi surfaces are locally nested, TC goes to 0. Okay, that's probably not true at finite coupling. It might be true for weak coupling. And this might give us, this is the only parameter we know that might give us access to the bare metallic quantum critical point. Okay, so without having superconductivity intervene. In particular, there's a beautiful theory by Peters here and Sang-Sik Lee that predicts for the O3 antiferromagnet a new type metallic critical point. And this is the parameter that we hope it might allow us to access that physics. Okay, so this is the same TC, but now as a function of the coupling strength. So we wanted to see how TC depends on the value of the coupling. So you see that for a small value of the Yukawa coupling squared, it looks like it's linear, and then it saturates at some value of lambda squared, which is of the order of the bandwidth. Okay, interestingly, this lambda squared is again what you get from naive Erez Berg theory, which seems to work surprisingly well for this problem. Right, one more thing we looked at in this context. It's been proposed that the same antiferromagnetic fluctuations that promote superconductivity close to the critical point can also promote charge order. And in particular, it turns out that if you linearize the fermion dispersion close to the hotspots, which is a common starting point for these theories, there's an exact symmetry, emergent particle-hole symmetry, that actually relates superconductivity and charge density wave fluctuations. So these two order parameters are exactly degenerate at that point. The system actually has a higher O4 symmetry. So it's been proposed that antiferromagnetic criticality is the ingredient basically to get both superconductivity and charge order. So we've studied that problem in quite detail. Okay, so in particular in our two-band model, it turns out that if you tune to particle-hole symmetry, indeed there is this exact symmetry relating charge order and superconductivity. Okay, so of course to do the simulations, you don't have to have particle-hole symmetry. So you can go away from it, but you can keep the perfect nesting. So you can have a perfectly linear Fermi surface, but not exactly particle-hole symmetric. So we've studied both of these type of situations, and also just breaking particle-hole symmetry weakly close to this point. And it turns out that this degeneracy between charge order and superconductivity is extremely fragile in the presence of small breaking of particle-hole. So for instance here, these are actually results for the straight Fermi surfaces. And even though the Fermi surface is perfectly nested, which you would think is as good as it gets for charge order, you see here the inverse charge order susceptibility and the inverse superconducting susceptibility as a function of temperature at the critical point. And they're not really close to being degenerate anywhere. Okay, so there is some enhancement of this charge order susceptibility, but it's quite mild. And below TC, you see this upturn. This is the inverse susceptibility, so that means that the charge order actually gets suppressed because the superconductivity is gapping out the Fermi surface. Okay, so right, so in the last maybe 10 minutes, I want to talk a little bit about transport. I started from this picture of the exponent of the resistivity that, as a function of temperature, that seems to have a very strong signature of the quantum critical point. Namely, it has linear T resistivity, which, as you know, that seems to be a recurring property over many materials. So we're very interested in the transport properties close to these critical points. Unfortunately, the resistivity itself is something that we cannot measure directly in our simulations, even if we don't have a sign problem. And the reason is that our simulations are done in imaginary time or Matsubara frequency. And we have to do analytical continuation to get the resistivity, which is basically as hard to do as solving the sign problem itself. Okay, however, we can get some information directly about the optical conductivity, sigma of omega, from the imaginary time data. Okay, so it turns out, for instance, we can define a quantity that we call the resistivity proxy, which is defined in terms of lambda, the current correlation function, in the vicinity of imaginary time equals beta over 2. Okay, so it's this ratio of the second derivative of this quantity at beta over 2 and lambda squared. Okay, and that turns out to be exactly related. I haven't written the prefactors here, but this is an exact relation. It's equal to the ratio between the second moment of sigma of omega, where the integral is taken up to an energy of order temperature, divided by the weight up to temperature squared. Okay, so this particular ratio of moments you can extract directly. And now if you make a further assumption about the form of sigma of omega, for instance, if sigma of omega is a single Lorentzian peak, then this basically, in combination with lambda itself, this gives you a weight and a width. And from that you could extract also the height. So that would give you the DC resistivity. So under that assumption, for instance, this just becomes, this proxy just becomes rho DC. So what I'll show you is really this proxy. But one has to bear in mind with this caveat that associating that directly with the DC resistivity involves this extra assumption. And right now, we don't have an independent way of checking that assumption. With that in mind, okay, this is what this proxy looks like across the phase diagram for the Ising-Nematic critical point, where we've investigated it in more detail. What's shown here is just the value of the proxy in natural units, h bar over e squared, as a function of the Turing parameter h and t. So the most striking thing here is that this resistivity proxy indeed knows very well about the quantum critical fan. So if you interpret this as the DC resistivity, it is very strongly enhanced in the vicinity of the critical point. Okay, and I'm drawing it here along these three cuts. Okay, the blue is crossing through the ordered phase. The green is in the quantum critical regime, and the red is far away. And you see that the value of the resistivity is much higher at the quantum critical regime, and much lower away. With some loving eye, you can draw a straight line through this, but there really isn't enough data to tell.
Erez, so h over e squared in those units, I suppose, is essentially the Montiel-Verger limit, or not?
Essentially, yeah.
So
it depends on whether you put the 2 pi or not.
Yeah, okay.
Yes, right.
But
So you would say 1 is like
that's right.
the Verger limit.
So so this limit is reached at a surprisingly low temperature above the critical point, right?
Yeah. So
0.5.
right. Yes.
0.5 T. Yeah.
Yes. Right. So let me mention, this simulation is for the strongest value of the Yukawa coupling we've gone to. We've also measured this resistivity proxy for weaker coupling, and then the value is much smaller. Okay, it's quite a bit below the Montiel-Verger limit, but it still looks pretty linear.
Okay. Yeah, that was my question. Can you get linear theories?
Yes. Yeah. It's actually more nicely linear. It's actually much more nicely linear in the weaker coupling. Yeah, but I don't have it. I can show you. Right. Yeah. So this result, if you believe that this is DC resistivity, is actually a surprise. It's a surprise for a few reasons, but mostly because the Ising-Nematic order parameter is a q equals 0 order parameter. So the critical fluctuations, by definition, occur close to q equals 0. So they can scatter the fermions very strongly, but when they come into transport, they always involve this 1 minus cosine of the scattering angle factor, and that should suppress their contribution to the resistivity. Yeah.
So a quick question for the red line. Can you extract a power on that?
Yeah. So to the extent you can, it's definitely not 2. Okay. So kind of the nice Fermi liquid behavior is something that we don't see. We have excuses for that, but at the end of the day, we don't see it. Okay? Yeah. Question? Was and still is a puzzle for us. Okay, so right. we have less, but some results for the antiferromagnetic case, and they actually look qualitatively similar. So the point being, the resistivity is enhanced very strongly close to the quantum critical point, and it's kind of quasi-linear there. Okay, so in the last few minutes, I'll just like to show you some more recent results, which are our attempts to understand the transport results I've shown you. Okay, so one thing we realized is that back to this diagram from weak coupling, that there is this broad regime where the bosons are strongly Landau damped, but the fermions are still coherent, where we can actually do controlled calculations. In particular, we have the fermions scattered off these bosonic fluctuations, and we can calculate transport. Okay, so that's what I'd like to show. I won't go into how into the method. It's probably it's basically some variant of Boltzmann transport, because the fermions are coherent in this regime with some modifications because of the form of the scattering. Okay, but let me skip the details here. Okay, at the end of the day, there's some kinetic equation that we solve, which is like the Boltzmann equation. But let me show you some results. Just before I do that, let me just mention, okay, so this is a translationally invariant problem. So the only way to get a finite DC resistivity is Umklapp scattering. So what we expect for the Ising pneumatic problem that we looked at so far is that there's an important momentum scale, which is basically the distance of the Fermi surface to the Fermi surface, to the closest point of the Fermi surface in the next zone. Okay, so I call this Q naught. This is basically the minimum momentum transfer that you need in order to do Umklapp. So we expect that if we go too close to the critical point, that the wave vector of the critical fluctuations goes below this scale Q naught, basically the critical channel would not contribute to transport anymore, and we would go back to the Fermi liquid T squared. Okay, so at low enough temperatures, it should go to T squared, even right at the critical point. Okay, so this has been known. Moreover, at finite temperature, this Q naught would have some temperature dependence that you expect to be of this form. So there's some crossover temperature that scales like Q naught to some power z, some dynamical critical exponent, where this crossover to T squared would occur. Okay, let me make in passing a comment. Okay, this is true for a hole-like or electron-like metal. In a compensated metal, for instance, this iron-based superconductor that I've shown its phase diagram before, it turns out that this consideration actually doesn't hold. So there you don't need Umklapp. Even in a translationally invariant system, you actually don't need any Umklapp to get a finite DC resistivity. So there we expect that T naught would be 0. Okay, so you might get anomalous transport all the way down to T equals 0 at the critical point. Okay, so let me show you some results. The results are for a large Fermi surface that looks like this. So this is the resistivity as a function of temperature right at the critical point. Okay, so and this is our T naught. Okay, it's not very well defined, but this is some temperature where we see a crossover to T squared. This is the log derivative of the same curve. Okay, so it starts from below 1, and it grows gradually, and you can't see it here, but eventually we've checked that at very low temperature it actually saturates at 2, as we expect. Okay, so you can pass the straight line here, but it's not really linear. You see it here. There's nothing special about linear. Linear is just the inflection point, right? So it goes from curving one way to curving the other way. Okay, and it looks like we've done this for various values of Q naught, various sizes of the Fermi surface. And it looks like this crossover scale defined operationally just as the temperature at which this derivative reaches some arbitrary value, that T naught scales like Q naught squared. So it looks like the dynamical critical exponent we should use here is 2. Okay, so this just comes from the behavior of the correlation length as a function of temperature, which has z equals 2. Okay, with this we basically infer from the numerical calculations. This is something we put by hand in this calculation. Okay, and these are some more results. This is the value of the DC resistivity as a function of distance from the critical point and temperature. So you see this very strong enhancement close to the critical point. This is what it actually cuts through this diagram look like. And this is the log derivative on the same plot. So you see that the exponent is kind of drifting slowly, and it does reach 2 at very low temperature. Okay, but again, the crossover temperatures can actually be surprisingly low. Okay, so there's some more results. We've tried to see what happens when you add a weak disorder to this problem, and it turns out that even at the critical point, Matheson's rules basically hold, so we can add the scattering rate. Elastic disorder just shifts these curves up by some constant. Okay, so that's it. Let me just conclude. The main point, I think, that we learned from these studies is that we can actually access quantum critical points in metals using numerically exact quantum Monte Carlo simulations. Okay, some of the lessons we've learned so far. So it looks like very generically that the actual metallic quantum critical point is preempted by some form of superconductivity. But we can look at the quantum critical regime above TC, and that shows us that there is indeed a quantum critical regime, meaning that the correlations grow very rapidly. There's some sort of breakdown of Fermi-liquid behavior, although not of the expected type. Okay, and the transport is very anomalous in this regime. Now, in terms of the correlated materials we're interested in, okay, there's several things that unfortunately seem to be missing in these models. So there's no physics of competing orders in the sense that other than superconductivity, there are no other emergent order parameters that compete close to the quantum critical point, like charge order. So meaning that these don't emerge as naturally as superconductivity out of quantum critical fluctuations. And there's no pseudo gap, meaning that if we look in this regime, it's we call it a non-Fermi liquid, but there's no gapping out that extends far above any ordered phase. Okay, so we don't see anything we can associate with a pseudo gap. Okay, here are some more thoughts. To my eyes, a lot of what we're seeing can be associated with this picture, okay, but that's somewhat subjective. This picture, strictly speaking, is weak coupling, as in our calculations are not, so it's not obvious. Okay, there's some questions here about comparisons with experiments, but I'll let you read. Right, thank you very much.